Hello everyone, good morning to everyone. On behalf of the IEEE San Diego section, I welcome you to San Diego. If you have any complaints, right, tell me, I'm the section chair. We'll make sure it doesn't happen again, but I think the weather came through well. And I would like to take this opportunity to thank the volunteers from the local chapters here in Southern California, the San Diego chapter, the Irvine Orange County chapter, the Foothills chapter, the Buena Vista chapter, for contributing their volunteers and the time over the last 4 years to making sure that this program is a gorgeous success. So while I wait for these party to depart here, we hopefully will have the stage to ourselves, and I can introduce you to my gorgeous friend from another fellow Brit, right? So if you can't handle my accent, you'll have to, he's got another twist on it. So here I'd like to take this opportunity to introduce you to Dr. Kenneth Stewart. Actually, he likes to go by Ken Stewart. Dr. Ken Stewart is a graduate, undergraduate and postgraduate degrees from the University of Strathclyde in Scotland. Ken is an Intel Fellow running the Intel Platform Group. His role is in the contribution of 5G LTE 802.11 systems, wireless system on a chip solutions, cellular connectivity solutions, and transceivers, codecs, radio access, offloading, routing, and of course my favorite, location systems. Let's give a warm welcome to Ken. Ken?
Thank you. Thank you. So good morning. I think that's the first time in my career I've been introduced as gorgeous, although I'm happy to have that accolade. So I'm Ken Stewart. Let me get started. You can pull up my slides, please. So when I first ran this presentation past Intel Legal, their first comment upon seeing the word future in the presentation was, you can't talk about the future, that's much too dangerous. Their second reaction was then to fall back when I refused to accept that advice on the Intel Attorney visual acuity function, which means they have a capability for very small font that you'll see at the bottom of the slide, which says basically that these are my own comments and not those of Intel Corporation. This, of course, gives me completely plausible deniability about anything that I say next. Thirdly, and most perhaps most importantly, they always rely on the fact that I have an outrageous Scottish accent, so most of you won't understand anything I'm saying anyway, which is the most appealing method of legal control that they have. So with that in mind then, let's continue with my thesis today, and I want to be a little more pragmatic today to talk about the pragmatism of 5G. How do we actually make money out of 5G? And the motivation appears on the screen. The reason why most of you are here, or at least many of you are here, lies in the data on this screen. On the left-hand side, we have subscriber growth rates. In this particular example in North America, over the last 25 years, we've gone from no subscribers to 300 million subscribers in North America. We have SIM credentials for almost every person on the planet. This has been a fabulously successful industry. The cellular model has been astonishingly effective at generating wealth. On the other side, the center data piece, the pie chart you see is of the fraction of traffic passing over Wi-Fi based networks of the total wireless internet. Depending on who you access, between 60 and 80% of the traffic is over Wi-Fi. There are, according to some estimates, 45 million public Wi-Fi hotspots in the world today. Again, a phenomenally successful business model, delivering huge value. Taken together, the total value of all the goods and services of the industry we take part in is somewhere between the GDP of Germany and France. Taken together, we would be in the top 5 of a geo-economic summit. So this is an incredibly wealthy, wealth-generating industry. And our mission, therefore, as we go into the 5G era, frankly, is how not to screw that up, is how to continue to generate terrific wealth in the service of both ourselves and of the planet. So how could we approach that problem is what I'd like to speak about today. Now, in the words of Charles Dickens in the opening lines of A Tale of Two Cities, he says, it was the best of times and it was the worst of times. So for the cellular industry and for Wi-Fi today, we have the stick part of 5G. That is the motivation, the imperative to change. And most of you will be very familiar with this. We have a problem with data explosions, 60 to 100% compound annual growth rate in traffic. We have the need to reduce the cost per bit transfer because revenues are not increasing on a per user basis. We have the need to accommodate an ever-increasing population of devices on the same networks. And we have the imperative to create new growth opportunities, new services from which we can extract value. So those are imperatives and frankly a crisis facing networks today. On the other hand, we also have the beginnings of some fabulously interesting technologies that can drive our industry for the next 30 to 40 years. We have the appearance of ever more advanced video coding, 4K and 8K coding, the possibility to deliver the voxel cloud to the device for a fully immersive remote experience. We have vertical markets appearing with aging populations in healthcare. We have the possibilities of sensing city landscapes for traffic, for energy consumption, for resource consumption. The global climate community is meeting in Paris as we speak, and this industry could lend the planet enormous service through the IoT capabilities that we have latent in the technologies we can bring to bear. So if you look at the opportunities ahead of this industry in enhanced mobile broadband, in massive machine-type communications, in mission-critical machine-type communications, we have an enormous opportunity and an incredibly interesting opportunity as well for those of us whose careers have been embedded in the process. Now, some very diligent people have been talking about requirements for 5G, and I think for the last 2 years, many of us, if not all of us, have listened to talks about requirements for 5G. And the best part is that now we're beginning to move from requirements to execution. But the requirements, just to restate for the record, we're looking, for example, at 20 gigabit per second throughputs. We're looking at edge latencies of less than a millisecond. We want system bandwidths of at least 100 megahertz. We want spectrum support up to 100 gigahertz. And we're basically inventing systems to be deployed in 2030 and beyond. We're inventing systems today that we will be using in 40 years' time. So the question therefore comes, let's not talk today about requirements. Let's talk about what is it we need to put in place to take action to generate the wealth and the revenues that we need to generate to sustain us into the future. So from my personal perspective, and channeling Intel Legal again, these are my personal views, there are 5 things we need to put in place. And they're very, very straightforward. Technical specifications, so in other words, do we know what 5G systems to build? Technical viability, have we established how to construct those 5G systems? Spectrum, do we have clearly identified spectrum that's available over the next 5 years in which we can deploy 5G systems? Do we understand the radio channel in which we will deploy those systems? And finally, do we have our act together to create a well-established timeline against which we can act, an action plan for delivering 5G. So if we do all these 5 things, we'll be in great shape. We'll execute the 5G plan we need for 2030 and beyond, and I will then be able to rely on the rest of you to fund my retirement, which is my objective today. So let's look at each of these issues in turn. How are we doing? What's our scorecard for each of those topics? So let's talk about technical specifications. What are likely to be the critical and crucial technical specifications for the 5G era? And they're relatively, I think, relatively self-evident for those of us who've been in the industry for a long time. LTE as a cellular technology has been enormously successful. There's absolutely no reason to believe that it will not continue to do so. It's a powerful vehicle for innovation, for deployment, and for the creation of services and wealth. At the same time, Wi-Fi, as I mentioned at the start, a phenomenally effective and useful means of communications. At Intel, again, my personal view, we expect both those technologies to continue powerfully into the future. But there are some very interesting trends around the edge. There are IoT systems beginning to appear below 1 gigahertz, especially given the propagation properties we have below 1 gigahertz. And we have the brave new frontier pioneered by 11AD and WiGig to push wireless communications far beyond the regions we operate in today, into the millimeter wave spectrum and centimeter wave spectrum up to 100 gigahertz. So if you analyze those trends, and if you look at and recognizing that there are a lot of excellent companies who are proposing and producing proprietary specifications or local specifications to meet these trends, it seems to me that there are really 4 preeminent vehicles that we will use in the 5G era to encapsulate our innovation and bring it to market. And they're enumerated on the right-hand side of the chart. So you'll see them as LTE-A Pro, which for those of you who may not be fully up to speed is the most recent instantiation of LTE, so LTE-Advanced Pro. Some kind of a new 5G RAT, or radio access technology from 3GPP, .11ax from 802, and .11ay from 802. So from the Intel perspective, we don't see 5G as being a single monolithic technology. We see multiple threads extending into the future, past 2020, and being deployed against specific use cases, and sometimes in a competitive fashion, to extract wealth and to generate economic value. So let's take each one of them in turn. What role might each one play, and how do they play into that broader ecosystem? So LTE Advanced Pro, so expected innovations, many of them nominally 5G innovations, and therefore this is definitively a 5G era technology. We have multi-site MIMO, beamforming, lightweight protocols, RRC protocols to enhance IoT access. We have latency reduction efforts. We have efforts around shared spectrum access, augmented spectrum access for access to unlicensed systems with LAA extensions. We have vehicle to vehicle. We have vehicle to infrastructure. We have all those innovations coming along. So this is an outstanding vehicle for the future. And it can achieve at least some of the key properties of 5G. For example, today, a typical state-of-the-art LTE modem today in the downlink would be operating at a peak rate of 450 megabits per second. Category 9 is the label that's attached to that. Category 16 is the device type that's being defined today with a peak data rate of just over 1 gigabit per second. Now, when you look at the nominal, simplistically calculated peak rate that LTE is capable of, with an 80 megahertz bandwidth on the downlink, assuming 4x4 MIMO and 256 QAM, you can achieve a data rate of 1.6 gigabits per second. And if you have available 160 megahertz, and if your device can sustain that bandwidth, you can get as high as 3.2 gigabits per second. Now, you might ask, how would an operator, how would a cellular network operator deploy and enable those kind of bandwidths? And it's clear that one can see a variety of mechanisms by which one can arrive at those available data rates to an LTE device. For example, for the 80 megahertz case, an operator might take, say, 40 megahertz of licensed spectrum, 40 megahertz of plus 40 megahertz of 5 gigahertz unlicensed spectrum to generate a total aggregated bandwidth of 80 megahertz. Very straightforward. For the 160 megahertz case, which is a little more adventurous, the same operator might take, say, 40 megahertz licensed, plus 40 megahertz licensed from 5 gigahertz unlicensed NII bands, plus 40 megahertz or 80 megahertz from 5G unlicensed, and 40 megahertz from the newly minted 3.5 gigahertz citizens band radio service, giving you a total of 160 megahertz of bandwidth. So these are very pragmatic, very available systems for radio resource allocation to achieve 3.2 gigabits per second with LTE today. So LTE is therefore nudging up against the nominal 5G target as a mobile broadband technology. And further, the innovations we're putting in place today in Release 13 enhances LTE's ability to deliver for the massive IoT or massive MTC model that I described at the start of my presentation. Two clear examples after the RAN 1 meeting 2 weeks ago. In Release 13 alone, we have the appearance of 2 instances of very low cost, low die size, low quiescent current drain MTC solutions for LTE. We have the category M or LTE-M solutions, data rates up to 1 megabit per second and a 1.4 megahertz bandwidth, supporting link budgets up to 155 dB at 23 dBm output power. So a very nice initial LTE-based MTC architecture. And we also have the further enhancement down to a 200 kilohertz bandwidth, the narrowband IoT specification that can operate in-band in an LTE carrier, it can operate in guard bands, it can operate on a standalone basis, and offers the possibility to remine 2G and even 3G spectrum to deploy wide area, massively capable MTC systems capable of supporting link budgets up to 165 dB. So again, LTE, even with the Release 13 innovations, is nudging up against the targets that we nominally set for 5G systems. So if we look then at the second specification that I mentioned, the 5G new RAT specification, what does it have to do to deliver truly distinctive value over and above what LTE can do, even in Release 13 and beyond? And I've listed some of those today. You see on the screen a nominal view of what we might achieve in Release 14 and Release 15 and what we might do in Release 16. But fundamentally, in Release 14 and 15, we might target, for example, data rates up to 20 gigabits per second, the ability to support spectrum from sub 6 gigahertz up to 40 gigahertz in an initial tranche that would support our ability to linearize millimeter wave power amplifiers and achieve effective cost points and benefit from centimeter wave propagation. A unified support for the enhanced mobile broadband use case, but looking forward, as we're developing and deploying LTE-M and narrowband IoT, the ability to extend the system into a future mission-critical and massive MTC system. Other innovations, massive MIMO, cell virtualization, leading to a second phase where we can become even more aggressive, tackle bands up to 100 gigahertz, possibly even beyond, into one of the absorption bands above 100 gigahertz, the possibility for new waveform optimizations to enhance millimeter wave device efficiency, and the possibilities beginning to emerge now of effective full duplex operation for wireless systems. So this is a much more aggressive form of 5G than LTE can sustain, but it truly augments the foundational layer we can build with LTE. Now, the economic model that IEEE systems offer, the Wi-Fi economic model, has been an incredibly powerful engine for wealth generation. As I said at the start, there's absolutely no reason why that can't continue into the future, and it should continue into the future as a key enabler for enterprise systems, for low-cost systems, and for non-centralized systems. And the .11ax project is making some extremely interesting strides to refresh and enhance Wi-Fi into new use cases. There's some nice changes to numerologies, some CP, some cyclic prefix optimizations, subcarrier separation optimizations. Of most critical interest is the ability to handle and innovate for the first time with IEEE 802.11 on a frequency domain multiplex basis, scheduled OFDMA, allowing better granularity of allocation of radio resources in the frequency domain, better range extension for IoT applications, and the critical low-cost enabling of mission-critical and key local IoT transfer for Wi-Fi with range extension. These are great enhancements to .11ax, and we expect Wi-Fi to continue strongly into the future on the basis of this new variant, a new amendment for .11. And then last but not least, in the unholy quadruplet of air interface specifications is the .11ay spec. This specification is of course the follow-on to .11ad. It's the successor for WiGig. Important innovations coming in multi-user MIMO, in single-user MIMO, at millimeter wave for WiGig, and the possibility of channel bonding as well. So again, a very nice innovation in the IEEE domain. Now, when I first joined Intel, I was instructed in my first day that any presentation that I made on behalf of Intel, even if it was plausibly deniable from the legal perspective, had a mandatory requirement to mention process nodes at least once. So as part of the third element I mentioned, do we have a means of realizing those 4 5G era systems in a cost and energy effective fashion? Now at Intel, we're currently working through in production in 14 nanometer technology. We're moving in research towards the development of 10 nanometer and the fundamental research of advanced process nodes around 7 nanometers. We don't see an end to Moore's law. We see transistor geometries. In this case, the graph in the center is logic cell geometries continuing as before. It's been an extraordinary journey since, in this case, since 1979. We've gone from just under 10 micrometer gate resolution to 14 nanometer, 1,000-fold improvement in transistor densities. So that, we believe, will help us with die sizes and sustain the die sizes we need to deliver for any of those 4 5G era technologies into the future. The graph on the right-hand side, though, is a little more interesting. Given that battery technologies are not improving radically, maybe lithium-ion improvements in energy density might be 7%, 8%,